Hello everyone, my name is Vikas Kumar Singh. I am a PhD student at Indian Institute of Science, and we are here to discuss the assignment of online course which is going on SWAM website, that mechanics of metal forming. So that course contains the theoretical part, and after if you are attending the course, you might be seeing or you might be aware with the assignments and all. So here. We are solving the assignments. Already we have solved 5 assignment, and today we are going to solve sixth assignment. So I hope you are familiar. So we will proceed with assignment number 6 today. This is from the this is one of the assignment where all the concepts before what we have discussed is mixed. So forming, bending is there, stretching is there, tensile testing is there. All mixed problems are there in assignment number 6. So let us start with assignment number 6. So we have, yeah, okay, one more thing, like in our assignment number 6, oh, sorry, assignment number 6, yeah, assignment number 6 and assignment number 7. So many objective questions are there, multiple type question, MCQ. So I have skipped few questions, like very simple questions are there. So I just thought I should focus on mostly on the numerical problem because they are having much deeper concept as compared to the MCQ question. So few of them I have just ignored them, and few I have considered which I found like that is important. So we are starting with one of the MCQ question here. So here, the first question is during seat bending with tension, the axial strain of the fiber at some distance from the middle is composed of membrane strain and. So in this question, the ask means it is asked when axial strain of the fiber is there in a seat bending. So that axial strain is composed means simply it is the sum of which two type of different strain. So one is membrane strain and another what is that? So we have to give one out of this four. So obviously the axial strain is composed of or sum of you can say membrane strain and bending strain if you have studied the theoretical part. So I will just give you a few bold point in a seat bending with tension. In seat bending with tension, the total axial strain at any point through the seat thickness is the sum of membrane strain and bending strain. Okay, so membrane strain is what? Uniform strain across the thickness due to axial tension. Okay, and bending is linearly varying through the thickness due to the curvature. Like suppose you have a sheet like this, okay, and you are bending it, so bending like this. So bending like this. So in this case, linearly varies linearly through the thickness due to curvature. So throughout this thickness, your bending strain will change. Okay. Therefore, the correct and complete description of the axial strain is sum of membrane and bending strain. So it's a very simple question. So moving towards the next question. So this will be the correct option, D. So the next question, in plane strain bending, the strain parallel to the bend will be what? So this is also one of the objective MCQ question only, and we have 4 options here. We have to choose one. So in a plane strain bending, obviously we are knowing the strain parallel to bend is 0. So this will be the correct. But what is the explanation? How to explain this? So I have given some highlights here. In a plane strain bending, no one direction, typically with the width direction, is constrained in a plane direction, in a plane strain bending. It means what? It means if it is constrained in that direction, there is no, means there, we are not giving any strain in that direction. This is the meaning of like plane strain. width direction we are not giving. So suppose like we have a seat like this, seat, a long seat is there like this. Okay. Here it's little confusing. So forget about this. Forget about this. You just one direction is constant, meaning no strain occurs in that direction. So suppose this is the thing. So and if we are bending about this axis, if we are bending about this axis, so this line means this face will bend. So this will become something. If you will see from here, if you will see from here, so this is going to be like this. Okay, this is going to be like this. So if you are we are seeing from here. So what is happening in this direction? In this direction, we are not giving any strain in this direction. Means if you are seeing from this will be this will be looking like this only. This will be looking like this. There is no any strain we have given to this direction. Okay, so this is what it is written here. The strain parallel to the bend refer to the direction perpendicular to thickness and along the width of the seat, which is restrained in the plane. That's what I explained here. Therefore, a strain in that direction is 0. Correct? Now moving to the next question. Again, a very simple question is there. For a seat following rigid, perfectly plastic model, sigma 1 is equal to, we have to choose one out of 4. So for a seat following a rigid plastic, rigid perfectly plastic. So it's nothing but a plane strain flow stress equal to that. But how this explanation we need. So the explanation is here. In a perfectly rigid plastic model, perfectly rigid plastic model. So we have several kind of thing, perfectly elastic, perfectly plastic. I'm sorry. Elastic plastic, elastoplastic is there, perfectly rigid body is there. So many, and all are defined by the hardening exponent like n, so that you know power law is sigma equal to k into epsilon to the power n, and n is defining all these different model. So according to that, in a rigid perfectly plastic model, the material behave elastically up to yield point, and then flow plastically at a constant strain, no hardening. What does it mean? Suppose you have a stress strain curve here. Okay. So you have sigma, you have epsilon. So up to yield point, suppose this is the up to yield point, this is linear, and then after that this is a constant. After that this is a constant. Means up this is plastic line, this is the stress, yield stress. If you are telling this is yield stress up to here, so this is this model itself is called rigid perfectly plastic. Rigid perfectly plastic. Okay. So next, in a plane strain condition, the material's resistance to deformation is characterized by plane strain flow stress. Plane strain flow stress. That is correct. Okay. Plane strain condition. We have to find out the plane strain and flow stress, which is typically higher than the uniaxial. This is also a correct statement. Now, since the material is rigid, perfectly plastic, sigma 1 is the major principal stress. Yeah, obviously it will be there, correspond to the flow stress and under the plane strain condition. So now I think it's clear that how this is happening in a rigid, perfectly plastic model, sigma 1. So this is equal to rigid plane strain flow stress definitely. So now this all three statements are connecting this thing. So I hope this is clear. Now we have the next question. So if the flow stress of a 2 mm thick, 2 mm thick sheet is 120 megapascal. What is the plane strain plastic bending stress? Keep answer in MPa. Okay. So here what is given there in the question, we have given the flow stress. So we have this flow stress in the question. Thickness is given 2 mm, not needed for this particular. Okay, leave it. I just have mentioned here. Required plane strain plastic bending stress in MPa. We have to calculate this. Okay. Now, you know the plane strain plastic bending stress is typically given by this formula is already derived in the theoretical class if you have attended that. So here I am not going to derive because we are limited with this time, and also just uh, take that formula. We can derive this also. It's already the derivation is there. If you are following the textbook that I have shared on Google Drive, you can follow the textbook. All this derivation is there. The main concept is, are you understanding the physical significance of this thing or not? Derivation and all, it's a mathematical calculation you can derive, but you must know what is the meaning of this, from where this is coming, how you are able to, either you are able to relate this thing with the actual problem or not. This is the important thing. So nothing is given here, just you put this sigma naught and you will get the answer here. So this is the final answer for this. And yeah, so this is also a very simple question. So now we are moving towards the next problem. Question number 5. What would be the moment of reverse yielding during seat reverse bending if the initial yield moment is 8.55 Newton meter? Okay, Bossinger effect is not considered. Choose the best. So here, Bossinger effect, you might be knowing that when we have a reversal stress, like one is going in positive, like suppose you have a seat here and you are putting the seat over here and you are applying a force in this direction and you are reversing in this direction, you are going in this direction, you are coming. So this is kind of shear reversal, and Bossinger effect is like when you are loading the material in a tensile. So and after some time you unload it, and then you come back. So this will go in a loop, something like this. So this is nothing but some hysteresis loss. So reverse Bossinger effect is some kind of, if you are loading and unloading and again you are loading. So how the stress strain curve will change. This is related with that. So here we are not going to consider the Bossinger effect. So because here reverse yielding is there, so that's why this effect came. And in question it is particularly mentioned, do not consider the Bossinger effect because of the reverse yielding, this effect is coming, so we have to discard it. So what is to be done now? We have to calculate the moment for reverse yielding. Moment we have to calculate. So here you can see for a reverse yielding in a bending, without considering the Bossinger effect, the yield moment in the reverse direction is typically half the initial yield moment. Okay. And negative because it's in the opposite directions. Like suppose you are going in this direction and when you are coming in this direction, so definitely if this is positive, then this will be negative direction. So nothing but you just have to this result from ideal elastic plastic behavior under the pure bending is half of the yielding moment, initial yielding moment. So simply just that yielding moment is given 8.55. So the half of the 8.55 will be your reversal moment, and minus is because the reversal is there. That's why minus is coming. So we just have to use this formula and we will get this. So this is the answer for this. It's a very simple question. Just you should know the concept, nothing. If you are knowing the concept, it will be very easy for you to solve all this kind of problem. So moving toward the next problem. Yeah, here is a very good question. a steel sheet is bent over a die block and then stretched. Okay, evaluate the fully plastic yielding tension in kilonewton per meter for the sheet with 1.5 thickness with constant uniaxial flow stress of 220 MPa. Its Young modulus is 200 GPa and Poisson ratio is 0.3. So in the question, it is given hint. You need to calculate the plane strain, flow stress, and plane strain Young modulus to find the value. So this question in the assignment itself, this hint is given. So that's why I have taken on. So here, one by one, we have to calculate. Like thickness is given, uniaxial flow space is given, Young modulus is given, Poisson ratio is given. And what we need to calculate, like according to the hint, if you will see, we have to calculate plane strain Young modulus. We have to calculate plane strain flow stress, and then calculating the tension per unit with Ty. So that is already in the previous assignment, we were discussing about the traction and all. So the traction or traction basically. So or sometime in the textbook also, the lecture also, this traction is called as tension per unit weight. So don't confuse about that. So this is nothing but the traction only. So Ty, and this is Ty is your sigma into thickness. So we will see like when we will come to this. So first we'll check the what is the plane strain Young modulus. So in the case of plane strain Young modulus, so we have to calculate, we need what is the Poisson ratio, and that formula is very simple. The given Young modulus divided by 1 minus Poisson ratio square. So it's a very simple if you are knowing this formula. So this will give a effective means plane strain Young modulus. Yeah. So we have the plane strain Young modulus if we are putting all this value. Now once we'll calculate this, we'll move towards the plane strain flow stress. And again, in the previous problem itself, we use this formula, plane strain flow stress, this one. So if here, here, this formula, if you are remembering, same formula we are using because same thing is asked in the next question again. So this formula here. Now we have to put this 220 value, that's all, nothing else. 220 is given. So we will get the plane strain flow stress now. Now the next is little important. So here we have to calculate the tension per unit weight. So what is that? So tension per unit weight, how we will calculate? So yielding tension per unit weight, the tension is calculated as I told, this is nothing but the stress into thickness. So here S is denoting whatever we have calculated previously here. S, this value, this is coming 254.034. So the same thing we are calculating and just taking the close value 254 for easiness of the calculation. And thickness, it is given in the problem 1.5 mm over here. So we can use that and we will get the Ty, this Ty value. Now coming to the point what is being asked in the question. Now converting this unit in Newton, we have to calculate kilonewton per meter we have to calculate. So this value is now converting the unit. So this value is going to come how much? If you will multiply this, we are going to get 381, and it's kilonewton means 1000. We have to multiply top, and mm is there in the bottom. So we just have to convert in meters. So 1000 we have to divide also. 1000 will cancel. So obviously we are getting the same value whatever is in mm, Newton per meter, Newton per mm, and kilonewton per meter, which is same. So this was the last question in this assignment, and few more questions are there that are objective questions. So I left that question because it's very simple. So what we learned today that again, like reversal bending, we learned reversal case, reversal, and we introduced the Bossinger effect, and condition of plane strain, plane strain, plane stress, plane strain, flow stress, condition for that. Okay, and yeah. And we learned about the bending. If a sheet is having bending, then what type of strain, what type of deformation you can say will come away from the axial line, like membrane and the first question I am just telling here. This was also very good recapitulation of your theoretical part, like this question. Yeah, here this question. During the sheet bending with the tension, the axial strain of the fiber at the some distance from middle is composed of the membrane strain, and the other one is the bending strain. So we learned all these concepts. So I hope everything is clear. So we'll stop it here because the assignment number 6 is having 6 and 7. Yeah, 6 and 7 mixed. If we'll mix it. So I have taken few questions from assignment number 6 and few questions from assignment number 7. And the remaining are objectives. So I have left that. Now assignment number 8 is there that we will solve. So now we will stop it here for today, and we will meet next with the new problems. And maybe in the next class, we can discuss some theoretical part also for clarity. So I will see you again in the next class. Thank you all for attending.